Hello everyone, my name is Talita Silva, and today I will present our article entitled Multitask LSTM for Arboviral Outbreak Prediction using Public Health Data. The authors of this work are Lucas Farias, Talita Silva, and Pedro Araújo. In this presentation, I will cover four main topics: introduction, methodology, results, and conclusion. So let's start. As we know, infectious diseases remain a major global health challenge, causing millions of deaths each year. They are caused by various pathogens and spread among humans or animals, with disadvantaged regions being especially vulnerable. When the number of cases suddenly increases in a specific area, we call it an epidemiological outbreak, which can put severe pressure on local health systems. This study focuses on Recife, the capital of Pernambuco, Brazil, chosen for its epidemiological importance and socioeconomic vulnerability. Arboviral diseases like dengue, chikungunya, and Zika remain a major challenge, and in early 2024, dengue cases in Pernambuco increased by 55%. Recent studies show that machine learning models, especially neural network and LSTMs, often perform better than traditional statistical methods for forecasting infectious diseases. For instance, GIA in 2019 and Sant'Angelo in 2023 reported improved predictions using recurrent neural networks and ensemble methods compared to regression and SIR models. Additionally, APSAR in 2020 demonstrated that LSTMs can accurately forecast COVID-19 trends, highlighting their importance for public health planning. Still, challenges remain with data quality preprocessing and overfitting, which can limit generalization. Our proposed approach is a multitask LSTM with two goals: outbreak detection and case forecasting. We trained the model using public health data from data sources and tested temporal windows for 60, 90, and 120 days. The main contributions are predicting multiple arboviruses simultaneously, assessing different window sizes, and demonstrating a practical application of machine learning on open government health data. Next, we move to the methodology, covering the dataset models and the multitask LSTM framework. To conduct this study, we used data from data sources and implemented LSTM and bi-LSTM models. For evaluation, we applied area under the ROC curve, F1 score, mean absolute percentage error, and median absolute percentage error. Finally, we performed statistical analysis using bootstrap and confidence intervals to ensure robustness. This slide illustrates the workflow of our proposed multitask LSTM framework. We start with scale epidemiological time series data and generate overlapping input windows of 60, 90, and 120 days. The dataset is split into training, validation, and testing sets, with training covering 2017 to 2022, validation using 20% of the training data, and testing using 2023 data, which was kept completely unseen. For model tuning, we use Tuner with random search, testing 30 configurations per window size, and optimizing layer units to minimize validation loss. The final models were trained with 5-fold time series cross-validation for 100 epochs, using early stopping and dynamic learning rate reduction to prevent overfitting. The multitask LSTM performs outbreak detection and case forecasting simultaneously, with predicted values to post-proceed via inverse normalization. For our study, we use epidemiological data from the Brazilian Public Health System, data source, specifically from the Notifiable Disease Information System, CNIN. This system provides structured records for 49 diseases, include 108 attributes such as species and demographics, age, sex, race, and case evolution, including symptom onset and diagnosis. We assessed and preprocessed the data using the PySUS library, focusing on confirmed cases of dengue, chikungunya, and Zika in Recife. The steps included filtering and municipality handling missing values and calculating standardized incident rates per 100,000 inhabitants. Here, I summarize the models. Recurrent neural networks are designed to process sequential data, but they face the vanished gradient problem. LSTM networks were created to address this issue with gates that allow the networks to capture long-term dependencies. This makes them effective for time series prediction. This slide illustrates the architecture of the two models. We implemented LSTM and BiLSTM. The BiLSTM differs by processing the sequence in both forward and backward directions, which can capture richer temporal dependency. For outbreak detection, we use two classification metrics. The F1 score balances prediction and recall, which is crucial since the outbreak data are imbalanced. The area under the ROC curve measures how well the model distinguishes between outbreak and non-outbreak periods, with values closer to 1 indicating better performance. For forecasting case counts, we use two regression metrics. Mean absolute percentage error measures the average percentage error between predictions and real values. Median absolute percentage error is it's a median-based version. It's more robust to outliers. Together, these metrics allow a reliable evaluation of prediction accuracy. We assessed classification consistency using 1,000 bootstrap samples, calculating F1 score and area under the ROC curve to construct 95% confidence intervals, providing a statistically grounded evaluation of reliability and uncertainty. Now let's look at the results and see how the model performed for outbreak detection and case forecasting. Here we see the forecasting results of the Multitask LSTM for dengue, Zika, and chikungunya. The blue line shows the reported cases, the yellow line shows the model predictions, and red dots mark outbreaks months. Overall, the model captured outbreak trends well, with dengue and chikungunya showing the closest alignment between predicted and actual values. These tables summarize regression errors. Dengue forecast achieved the lowest error, with the simple LSTM at 120 steps reaching a median absolute percentage error of 4.45%. Chikungunya showed more variability, performing best with short windows. Zika presented higher errors due to limited data, but still benefited from longer inputs. In most cases, the simple LSTM outperformed the bidirectional version. Where we present classification results. Here, we present classification results. For dengue, validation performance was very high, but declined when tested on using 2023 data. So, area under the ROC curve remained above 0.93. For chikungunya, results were more unstable, especially at 90 steps. Zika showed consistent behavior, achieving the best F1 score of 0.87 with a 6-step input. These outcomes highlight for how window size and disease characteristics affect classification performance. This slide shows the 95% bootstrap confidence intervals. For F1 score and area under the ROC curve, the intervals confirm that the model's results are generally reliable, but they also reveal sensitivity to sequence length and disease type. Despite this variability, the Multitask LSTM framework proved robust for both forecasting and outbreak detection. In summary, the results show that the Multitask LSTM can effectively forecast case counts and detect outbreaks, though performance varies depending on the disease and input length. Findings provide useful insights for improving surveillance models. Now, let's move to the conclusion, where I summarize the main contributions of this study and discuss future directions. To conclude, in this study, we developed a multitask LSTM for outbreak detection and case forecasting of dengue, chikungunya, and Zika. Combining classification and regression, the model captured temporal dynamics with performance influenced by input window length and show acceptable generalization for public health surveillance. Of course, this study also has limitations. It depends on data quality, faces challenges with class imbalance, and uses data from only one city, which limits generalization. For future research, we plan to include external data like climate and mobility, compare with other models, improve interpretability with techniques like SHAP, and benchmarks against classical methods to highlight the benefits of multitask learning. So, thank you very much.